Hi everyone, welcome to our Algorithm Seminar. Today we're happy to have Binghui here to give a talk. He's a Motawani postdoc at Stanford University working with Abia Rubinstein and Amin Saburi. Previously, he was a research fellow at Simons Institute on large language models and transformer program. He obtained his PhD from Columbia University, advised by Shichen and Christos Papadimitriou. He has worked on learning theory and game theory, and most recently, large language models. Please welcome our speaker.
Yeah, thanks for the introduction. And thanks everyone for coming to the talk. It's my great pleasure to present my recent work on theoretical limitations of multi-layer transformer. This is a joint work with my co-author Li Jie Chen and Hongxun Wu. Li Jie is a postdoc and incoming faculty at UC Berkeley. Hongxun is a PhD there. Okay, so transformer is the backbone architecture of a modern large language model. It's kind of used by every commercial language model. In this work, we focus on this transformer architecture, and we want to study it from a more theoretical perspective. In particular, we focus on the representational length of transformer. And the key question we ask is what functions can be computed or cannot be computed by a multi-layer transformer. Here's the outline of today's talk. So I'll first just spend a few minutes to give a brief overview of the transformer architecture to make sure we are on the same page. Then I will describe our results and some of its implications. And finally, I will give a high-level overview of the proof. So first, transformer. So typical transformer consists of multiple attention layers and MLP layers. Actually, it's alternating between attention and MLP layer. So roughly speaking, given it's a like sequence to sequence model. So give a sequence, it first goes through some attention layer, which used to exchange information between these tokens. And then at each tokens, it applies MLP on that separately. This is one layer that consists of attention and MLP. And then transformer stacks multiple attention and the MLP layer on top of each other. So the key innovation of transformer is the attention mechanism. And I will just give a quick description of the attention layer. So the input is a sequence which is of length n, and we assume each token or the embedding dimension is d. The output of each attention layer is another sequence of length n and dimension d. In particular, at each position I, the output at ith position is determined as the average over input sequence. In particular, here V is the value matrix, so the output at ith position yi is a weighted average of the value at position j. And here the key is to compute this weighted average of our ij, which is, I call it attention probability of token j. And this attention probability is calculated as the inner product between the query value at position I and the key value at the position j. And then you take a softmax over it. So this is the mathematical expression of it. So I intentionally omit one subtle yet very important detail here. So recall that the output token I is a weighted average of input token j. And here, you need to take a summation over our input position of consideration. The most natural one and is so-called full attention. That is, you take summation over all the input positions. That's called full attention, and that's how it works for encoder. And if you think view it as a graph, then this attention graph is like a complete bipartite graph. Another possible choice is the decoder architecture. In particular, the idea is that since the input, the sequence is usually like a sentence or some language, so it's very natural to just attend to our previous token, that is, tokens appears before the current one. In that case, the summation is taken over all position j that's smaller than I. That's these tokens appear before position I. That's so-called a decoder, and it follows an autoregressive generation manner. And here's the attention graph if you virtualize as a bipartite graph. Okay, so if you want to consider transformer, there are really many complicated empirical details. So transformer is not the only one that makes language model works. There are many details such as like tokenization, like how you prepare your tokens, like also position coding, how do you differentiate your input token, and also for the MLP layer, there are many subtle choice, like whether you want to do layer normalization, what's your activation function, and also it can sometimes it's also have some mixture of expert architecture inside of MLP. So there are really many details there, and so for theoretical work, we really want our result to work for regardless of this detailed empirical choices. And it's fortunate that in our theoretical framework, we actually do not need to care so much about these details, and I think they just doesn't matter for our purpose. In particular, if you want to consider the representation power of a transformer, and our results would apply to all these different variants of transformer. But there's one detail that's actually matters and very important. This is the difference between encoder and decoder, which I briefly described in the previous slides. So in terms of encoder and decoder, there are three important variants. The first one is the encoder and decoder architecture, which actually the one used proposed by the original transformer paper. The second variant is just encoder only. The most famous one is the BERT model. So recall, like for encoder only model, when you compute the attention layer, the output at position I attends to every input tokens. The third one is the decoder only model, where at each the output at position I is determined only by previous token. So the decoder only model is actually the one used by all modern language models like GPTs, Gemini, and Llamas, and so on. And also from a historical point of view, we see a shift from this encoder-based model like BERT to decoder model like popularized by GPTs. And nowadays, as I said, all this modern language model are in decoder-only model, and this is particularly aligned with their training objective of mass token prediction, and it allows like autoregressive generation. So the focus of this work would be on decoder-only transformer. Okay, next I will describe our result. And before that, I just want to set up the formulation of the problem we consider. So the view we take is that we think of transformer as a circuit, which is parameterized by four parameters: L, H, D, and P. The most important one is the L, which refers to the number of transformer layers. So when I say one layer transformer, I mean one attention layer and multiple MLP layers. Also, we assume there are H attention has the embedding dimension D is D, and the precision is P. That is, each neural network width is described in P bits. So from this view, transformer describe a mapping from input sequence to an output answer. In particular, the input is usually some sentence or some questions, and then the output, we just assume, is taken from the embedding of the last position, from the last layer of the last position. Okay, so this is kind of like the most standard and the classical formulation of the problems is well studied in the literature. So the advantage of this formulation is that kind of capture one-step computation of transformer. It's particularly suitable when you think of transformer as like a reward model, or like if you consider each token generation of one step is kind of like capture one-step computation of transformer, and it's good if you think of this as an oracle model. On the other hand, it kind of ignores inference time scaling. That is because usually nowadays transformers generate token by token. So actually, it allows output intermediate step. But in our work, we focus on the circuit view, and because it's capture kind of like one step computation of transformer, and it's useful when you think of it as a reward model or some oracle model. So let me briefly review the literature. So what has been studied there? So in terms of representation power, there are roughly two types of results. So for the first one is to study kind of the power transformer. It's like what task can be solved by transformer, transformer in principle. This usually involves some construction of the transformer circuit, and then showing that some functions of some tasks, so some functions can be approximated by transformer, or some algorithms can be carried out by transformers. So initially, it's people starting from like studying some regular language, but when we witness like transform become more and more powerful, people also study like in-context learning and other many other tasks. There's a second line of work which is actually quite similar to the first one. But it shows that the aim is to show that transformer has certain advantage against traditional sequential modeling architecture like RNN or STM, or some newer one like state space model. And so from a very high level, the idea here is usually you can just do some ad hoc construction of transformer circuit and shows that it approximates certain function well. The second law of results study the limitation of transformer, and that's what task cannot be solved by transformer. So the reason that we want to study limitation, because usually when we think of like what task can be solved by transformer, the only way we can do it just to construct the attention and MLP layer step by step. But in many cases, we actually do not know what's the most efficient way to perform this construction. And I think this is where this limitation view comes out. Like by studying the limitation of transformer, we can know what task cannot be solved by transformer and what's the most efficient way of constructing transformer. In terms of results, there are two types of results. The first type of results is about proving some unconditional lower bound for one layer transformer. I think probably the first paper is by at this line of work. The first paper is by Clayton, which shows like one layer transformer can now solve certain 3 sub problems. And later, people also extend the methodology to other tasks like function, composition, induction head, and many follow-up on this line. So the basic idea is to use some communication complexity tool to show limitation of one layer transformer. The advantage of this kind of result is that the result is not that is asymptotic and actually applied to many practical regime. But the downside is that the technique seems only works for really only work for one layer transformer. So every time you prove some certain type of result, you need to assume the transformer is only of one layer. So the natural question is how about multi-layer transformer? So it's natural. It's quite obvious. Like things could become complicated when you consider multi-layer transformer. There's kind of some speculation in the literature, at least as far as I can understand. There's probably some circuit lower bound barrier for this, but it's actually not quite formalized. So kind of motivated on this, there are works that try to understand multi-layer transformer using computation complexity conjectures. For example, people show that the computation of transformer can be captured by constant depth circuit or like log space computation, and also can be captured by the massive parallel computation model. Okay, so this for this type of result, they rely on some computation complexity conjecture, which is some problem that people study for many years, and people kind of have some good reason to believe that. But the downside is that this complexity conjecture is not proved, so it's still possible they are false. And also, in some sense, using existing computation model could be just too general to capture transformer. For example, if you think of transformer as TC0 circuit, actually not only transformer, but actually really lots of architecture belong to, as long as it's like the depth is small, it can be captured by TC0. So it actually reveals it does not reveal too much about the transformer architecture. Okay, so the main result of our paper is we prove lower bound, in particular unconditional lower bound for multi-layer transformer. So it kind of extend the previous work that previous unconditional lower bound for one layer to multi-layer, and without relying on any computational complexity conjecture. So a very short summary of results is that we prove that an L layer decoder-only transformer could now solve L-step sequential function computation whenever the width of the network is small. So here, when I say width, it's actually the product of this hidden dimension times the number of tension head times the precision, which is roughly the width of that tension layer. And so as you can see, this is a kind of asymptotic result. The result could hold for any constant L. And so in this asymptotic regime, our result implies that for a fixed L layer transformer, like it can only solve L step computation, but not L plus one step computation. Okay. So our result is for multi-layer transformer. It shows lower bound for L layer transformer. And the task, the kind of like the hard task faced by this multi-layer transformer is so-called composition task. And here is a formal definition of the problem. So the L sequential function composition is defined as follows. So the input consists of L functions, F1, F2 to FL, and a query W. So the W also consists of L parts. The task we consider is to iteratively compute the composition of this L function. In particular, we want to sequentially the definition involves sequential compute of L index. The first index I1 is just the value of F1 applied to W1. Starting from the second index, say I2, its value is determined by F2 applies to W2, that's the second part of the input query, and the result of the first composition, that's I1. So in the L step, the index IL is determined by the L function, and we want to apply it to WL and IL plus IL minus 1. Okay. And for finally, we just want the model to output the last index, that's capital L. So in the problem, we assume the input prompt explicitly describes the function in the reversed order of map. It first describes the function mapping FL, then FL minus 1, and Q F1. Finally, it's followed by a query W. And here's an example. So in the example, I will assume L equal to 3. So here L is actually the number of composition steps. So in this case, the query consists of 3 parts, W1, W2, W3. And in the example, I assume each W1, W2, W3, they are either 0 or 1. Recall the composition involves 3 steps. The first step is you obtain I1 by applying F1 to W1. And then you obtain I2 by applying F2 to W2 and I1, and so on. So if you look at this case, the domain of this function actually grows exponentially. For example, for the first function, it's a mapping from the input and output domain is actually of size 2. The second function, the input and output domain increased to 4 because F2 takes two parameters, W2 and I1, and F3 actually grows even larger. It becomes it's a mapping from 8 to 8. And in the prompt, we just describe F3 at the first, then F2, F1, and followed by the query. And here's an example. Assume the query W equal to 1, 0, 1. So W1 equal to 1, W2 equal to 0, and W3 equal to 1. So in order to perform the first composition, we want to look at which entry of F1 is relevant. So in this case, W equal to 1. So we should really look at the second entry of F1. And let's assume the second entry of F1, the index I1 equal to 0. Then this means at the second step, in order to compute I2, we should look at the first or the third entry of F2. And because W2 equal to 0, we should really look at the first entry of F2. And now, suppose we figure out the right entry to look at and assume the first entry of F2 equal to 2. This means at the third step, we should either look at the third entry or the seventh entry of F3. And because W3 equal to 1, we should look at the seventh entry of F3. And finally, the answer is just described in the seventh entry of F3. Okay. So let me give you a very high-level intuition on why this is supposed to be a hard task for transformer. And our key intuition is that when the important information is presented at the end of the sequence, then autoregressive transformer fails to retrieve information efficiently. It could still retrieve information, but they need to retrieve it in a step-by-step manner. So there's no like shortcut for this problem. And if you look at kind of like the computation graph, you in the previous example, you'll realize that F3 really takes part of very large fraction of the input sequence, and there's lots of computation down in F3. But because of the autoregressive nature of transformer, the computation is kind of wasted because the computation on the first on F3 actually does not involve any information from F2, F1 to W. So when the important information is presented at the end of sequence, transformer is inefficient, and because massive computation are really wasted at the beginning of the sequence. Okay, so I will describe the intuition and some proof in more details, but first let me just go through some implications of our main results. So the first implication is on depth and width trade-off. The L sequential function composition task can easily be solved by L+1 layer transform with only polylogarithmic width. So this means for composition task, depth could be more important than width and this shows that L+1 layer transformer could potentially be exponentially small, could have exponentially small width than L layer transformer for composition task. So is it true like in empirical? So from empirical observation, actually, from the scaling law paper of Kaplan, actually depth does not matter too much for pre-training loss, as long as you're not training a 1-layer or 2-layer transformer. Actually, depth does not matter. Depth and width ratio does not matter too much for pre-training loss. But recent study also observed that for some simple like multi-hop reasoning task, actually depth plays more important roles. And if you increase the depth, actually you can save a lot of this. So in this regime, depth seems to be important for certain tasks like graceful math and certain artificial composition tasks. So our results also align with this observation. So the second implication of our result is that there's this exponential separation between encoder and decoder. So these are really two different architecture. It's not hard to construct an encoder such that it could solve the L sequential function composition task using only log L layers and roughly polylog width. Because this shows like the expressive power of encoder and decoder could actually be very different. Though people already shift from encoder to decoder for many years, but I feel in the theory community, people still kind of study both models and maybe treat it in a relatively equal way. But our work shows actually they are very different, and in terms of representation power. In fact, we show that if you consider encoder-only model, we show that any depth L n+1 n to the 1 plus epsilon where symmetric circuits can be simulated by similar set transformer, that is L layer transformer with n to the epsilon. This means there's some circuit lower bound barrier for encoder, because in the complexity community, actually we don't know any non-trivial lower bound, even for linear size depth 3 symmetric circuits. This means if you can prove some lower bound against multi-layer encoder-only transformer, it would imply superlinear lower bound for symmetric circuit, which solves certain frontier which solves some open questions in complexity literature. Finally, I just want to briefly mention that now we all know that chain of thought paradigm is very useful, and the step-by-step reasoning could elicit stronger capability of language model. So in the test time, you should really let language model reason for multiple steps, and this would have stronger capability. So this is kind of weird by previous work. So people show like once with arbitrary long channel salt, transformer could simulate any polynomial time algorithms or polynomial size circuit. So if you assume TC0 does not equal to P, transformer with channel salt should have much stronger representation or computational power than the single step computation of transformer. So our work kind of gives an unconditional proof for this result because this L-step sequential composition can be easily solved by a one-layer transformer using L-step channel salt. So this gives shows some provable benefit of channel salt. Okay. Finally, I want to give a high-level overview of the proof and how we obtain the result. And here's a high-level plan of the proof. So the proof consists of two parts. The first part is more like some conceptual contribution of this work. We formulate a new model called a communication model. We call it autoregressive communication model, which we believe capture the computation of a transformer in a more precise way. In particular, we have a simple reduction showing that a communication lower bound of this autoregressive communication model would imply lower bound for transformer. The second part is more technical, where we prove communication lower bound under this autoregressive communication model, and we describe a new technique called indistinguishable decomposition. In this talk, I will mainly focus on the first part and showing why autoregressive communication model is it's a nice way to capture the computation of transformer. So here's the definition of autoregressive communication. This is a multi-party communication problem. In particular, we assume there are n players where the ith player receives Zi as input. So Zi could be a single token or it could be multiple tokens. The communication proceeds in L epochs, where in the L's epoch, the communication proceeds as follows. So for each player I among the n player, player I would first send some message to player J, to previous player J. So here, when I say previous player, I mean players I plus 1, I plus 2 to player I. Okay, so player I send message to previous player J, and then player J, based on its own information, and then the message from player I replies with some message replies with some message pi ji to player I. So here the information state we should define it very carefully. Initially, it's just defined as the input of player J. And once after this player performed the communication, player I would update its information state by including both the information state from the previous epoch plus the information received, plus the message received from the previous player. That is, the information state of player I is updated to include our message received from previous player, but it does not include any message received from players appears after it. So this is kind of key feature of this communication model. Though like player I and J transfers information mutually, player I would remember information transferred to player J. Oh, so sorry, the information gathered from player J, but player J will not remember information sent from later players. Okay, so I will give you an example to illustrate the model. So in this example, we assume there are 4 players, and there are 2 rounds of communication. So the 4 players, they receive Z1, Z2, Z3, Z4 as input. So consider the first round, first epoch communication. The last player, player 1 would first send a transcript pi 1,2 to player 2, pi 1,3 to gamma 1,3 to player 3, and gamma 1,4 to player 4. Then and this transcript gamma depends only on its own input Z1. Then all this previous player would respond. For example, the last player, the player 4 would respond with pi 4,1, which depends on its own input as well as the transcript received from sent from player 1. And similarly, the third player would return with a message pi31, which depends on its own input Z3 and then the transcript gamma13 and so on. Okay, after that, the information state of the first player is updated to include both Z1 as well as the transcript received from the previous player. Then player 2 would send transcript to previous player, that is player 3 and 4. So in this case, the transcript gamma 23 and gamma 24 depends only on Z2, but not depend on the message received from player 1. And then player 3 and 4 would return with transcript pi32 and pi42, which, for example, the transcript pi42 depends only on the input of player 4 and the transcript and the transcript of player sent from player 2. After that, Z2 would update the information state. It includes Z2 as well as the information, the transcript received from previous player. But importantly, it does not include the transcript it received from player 1. So finally, player 3 and 4 would communicate. Player 3 sends some transcript to player 4, and then player 4 would reply with some message pi43 to player 3. And then player 3 updates the information state to include Z3 as well as the transcript received from 4. And player 4 just updates its information state locally. That's one round communication, and the communication could proceed in multiple routes. Okay, so here the reduction is the follow. So we prove that a L layer transformer would imply some deterministic communication protocol for this under this autoregressive communication model. In particular, an L layer transformer would imply the communication protocol such that the information exchange between player I and player J at any epoch scales linearly with the input size of player I. So recall this gamma ij and the pi ji. It's just the information exchange between I and J at L's epoch. So transformer would imply such communication protocol, and the communication size scales proportionally with the input size of player I. So the proof is actually very easy. Essentially, using the transformer, we can construct the communication protocol as follows. So at each round, player I would just send the query value to player J. And then player J would return the partial sum of the attention probability and then the value and the value from ZJ. Okay. So here I just finished the description of this autoregressive communication model, and then show that actually communication lower bound out of this model could imply lower bound for a transformer. In the second part, I would give a very high level view on the communication lower bound. So I'll only leave some remark, and first I want to start with some intuition. So the intuition is like why we expect sequential function composition is hard. And recall like sequential function composition involves L step of composition. At each step, the index IL depends both on the L's function and previous index and then the query at WL. So the intuition is that without knowing the value of IL as well as the query W, the communication among FL plus 1 to FL is just useless. So before knowing IL, all the massive communication between L plus 1 to L, it's not useful for the final result. This is kind of similar to the round elimination idea in the communication complexity literature. So in order to formally prove the lower bound, the approach become more complicated. And the high level idea is we describe some useful technique called indistinguishable decomposition. That is, we want to find certain assignment of player of the first L-1 player and the second part of player, such as for every input drawn from this decomposition, or every input assignment from this decomposition, the transcript just look the same. They lead to the same transcript. And the second, we want to find a large indistinguishable composition, and we additionally needed the indistinguishable composition to have large coverage on the L-1 index. I'm happy to elaborate more details on this part, but high level, we just want to find some decomposition that's indistinguishable from the first L player and the second part of player. Okay, let me wrap up the talk and just give you some high-level summary of our work. So our main result gives the first unconditional lower bound for multi-layer decoder-only transformer. I discussed some implications on composition, multi-hop reasoning, and as well as it has some implication on depth width trade-off and some architecture separation between encoder and decoder. So I think for me, the key conceptual idea that could be useful to future study is the proposal of autoregressive communication. I think in order to study the model, communication model transformer, it might be beneficial to just start a new computation model, because transformer is really widely used in practice, and it's a good time to have a new model for it. And this autoregressive communication model can demonstrate these ideas. So by studying this model, we prove unconditional lower bound, and this lower bound is also stronger than previous work because it can show some depth width trade-off. And in terms of technique, we certainly borrows ideas from this field of communication complexity literature, such as like direct sum idea and the round elimination idea. And we develop some new technique for this model, but I think in the future, I would say I'm happy to see more techniques for these models. And I think we need more techniques on this model. Okay, yeah, I want to wrap up my talk here, and thanks everybody for attending my talk.